So let's go ahead and get started. Welcome back to MAT1841. Sorry, I'm a little bit late today. Well, last time we started talking about how to prove phase transitions for component sizes. And now these are going to be somewhat more difficult proofs because unlike the examples we saw last time of like diameter and isolated vertices, we're going to have to actually define some other process. It's not just going to be a matter of counting some existing phenomenon. So for isolated vertices, you just had to count them up and then use the first and second moment methods. For diameter, you had to count up some weirder type of phenomenon, but this phenomenon of bad vertices, and then you could just use the first and second moments. For this, we're going to have to do a slightly more complicated process, which we started describing last time. So the basic idea is we're going to imagine exploring a graph starting from some location. And the way it's going to work is you're going to start at some location, you're going to look around you to see which other nodes you're connected to as neighbors, and that'll be your frontier. And then at each step, you walk to one of the neighbors, you walk to one of the nodes in your frontier, and then you repeat the process. And you do this over and over again until, well, there's no more frontier left to be explored. And once you've done that, you've explored an entire connected component. And so what we've done is we've defined some sort of iterative process, the length of which is the size of a component. And so now if we can bound how long it takes for this process to terminate, then that also lets us bound the size of the first connected component we see. So that'll be our strategy. But now there's a slight problem here, which is our process is not well defined once you hit component size 0, right? So once the process terminates, it's no longer well defined. And so it's a little bit harder to characterize the values of this process. So what we're going to do instead is now we're going to modify this breadth first search so that it continues onward even after it's finished finding a component. And then what you do is then you just look at this function, which is well defined on all the nodes of the graph, so all the way through n. So this allows us to do more useful calculations, easier calculations on it, while upper bounding the size of the component. So what do I mean by that? Well, let's define this modified breadth first search. Sorry, let me bring up the chat in case people have questions in there. So we're going to define this modified breadth first search. Let's see, modified BFS. So this modified breadth first search. So normally the process ends when a connected component is explored, right? So normally process stops when connected component is found. Component is found. But we want our process to keep on going even after connected component is found. So any ideas?
So I'm not sure if this is what we want, but maybe you can like pick a node that's not in this component.
That's exactly what we do. We just randomly, arbitrarily, not necessarily even randomly, we arbitrarily pick some other node and we restart the process just over and over again. But we have to do this a little bit carefully so that we don't mess up the like component sizes and things like that. So instead, what we're going to do is the frontier is equal to 0. So this will be after you found your first component, or at the very beginning when you don't have a frontier yet. Then what we're going to do is we're going to create a new node, and this is going to be important. This is not a node we've discovered because it's not a neighbor of any node. But we're going to create a new undiscovered, and we're going to call it a red vertex. Connected to all other vertices with probability P, which we then explore to reach a new connected component. Okay, so this is clearly a well-defined process. It might have some weird effects later on because you're introducing these new nodes. But importantly, what this allows us to do is it allows the process to continue even after hitting an entire connecting component. And what's more, the first time the process that the process hits a 0 in the frontier, so the first time the process would have stopped is still when the process would stop normally, right? And we can let's see. So, oh yeah, go ahead.
Yeah, so is this new red vertex
Like, does it have an edge to every single other node probably P, or does each edge exist with probably P?
It has a connection to each individual other node. So each of the potential edges with probability P. So you should think of it as just augmenting your graph with an n+1 vertex that has all roughly the same properties, except that this is going to be some other node, and it's not going to be a node that we've already explored.
Okay.
Yeah. So instead of just picking some other arbitrary node, we're instead going to introduce a new node and then start exploring from there. And so this modified BFS has a nice property. Has the property let the probability a node is unexplored after I steps. Oh, sorry, undiscovered. Undiscovered, I think that's what I meant. After I steps is 1 minus p to the I. Why is that? Because at every single step, each step is an exploration of a single node, right? So at each step, you're asking from that node, can I reach every one of these other nodes? And so if some node is still undiscovered after I steps, that means that in each of the previous steps, you've asked, is it connected to that node you were exploring? And the answer to that has been no. And note that this is true, even note that this property is not true of the original BFS. Why? So let me give you a hint. What happens if the first connected component you find is of size 10? What's the probability that a node hasn't been explored after 15 steps?
Sorry, can you repeat the question again?
Yeah, so right now I claim that this modified BFS has this really nice property where you can figure out whether a node is undiscovered after I steps. And I further claim that you can't do this with the original BFS. And my hint is that suppose that the first connected component has size 10. What is the probability that some other node remains unexplored after 15 steps for the original BFS?
Is 0, right? Because you just walk around your component.
Yeah, so your process stops, so it's undefined. So I mean, it's either undefined or if you're continuing to walk around, it's 0. And so that's the issue, because with the original BFS, it's not well defined what happens after some number of steps, because you can only condition, you have to condition on when the termination was. And so that's a lot more complicated to compute. Whereas with this modified BFS, we can write down this easy explicit formula for the probability that a node is undiscovered after I steps. Because you never stop. And so that's the whole goal of this, is that you want a nice, easy to write down formula for the probability that a node is undiscovered.
At the end, the original BFS, the size would be kind of restricted to be less than the size.
Exactly. So like our formulas would just like fail after you got to I of them. And furthermore, the reason we can't just pick an arbitrary node is because then like it messes up this discovered probability, because you might have picked it without discovering it and then you just never discover it. Whereas with this modified BFS of introducing a new red vertex, we suddenly have the ability to give the probability of being undiscovered in this nice way, which then allows us to use moment methods, basically.
And just clarify, whenever you create this red vertex and you go to a new one, you don't sample going back to the red vertex ever, correct?
So that actually, no, so you fully explore this red vertex. And so it has a bunch of connections to other places as well. And so it's basically creating some new thing with a connected node that might be different than what your graph would originally have been. But that doesn't matter because we only care about the first stopping point, right? Because what we're interested in the size of the connected component. So we only care about when it stops first, or when it would have stopped first. And so what happens afterwards is of lesser importance, so long as the probabilities remain nice to compute. So let me be a little bit more formal about that. So for a graph, G of n d over n, because this is the phase transition that we're looking at right now, where probability of an edge is d over n. So d is roughly speaking the degree, the average degree of a node. well, P is equal to D over N, and we're going to define a new quantity. So earlier we had the size of a frontier, right? Now we're going to define, so in the past, the size of the frontier you could give as the number of discovered elements minus the number of explored elements, right? Because something's in your frontier, if you've discovered it, you see a link to it, but you haven't like gone to it and explored all the links around it. Now we're going to do the same thing, except I'm going to call this frontier hat, because it's no longer exactly the frontier anymore, right? Because this number can now be negative. So modified and potentially negative. Potentially negative because red nodes are explored but not discovered. Which was not true originally, right? So originally, if you were going to explore a node, you had to discover it first. But now that doesn't have to happen. And so this modified frontier size, in quotes, can potentially be negative. But importantly, this modified frontier size is of course related to the old frontier size. So actually, did I use a different notation? I think I did use a different notation. I think I did frontier prime. Okay. So what we're going to do is we're going to let Fi be equal to the size of frontier prime at step I. Well, then for large n, the expectation of Fi is going to be equal to n times 1 minus p to the I minus I. Basically, because this is the set of discovered vertices, and this is the set of explored vertices. Because at each step you explore a single vertex. And each step you discover approximately n times 1 minus p to the I. And this is approximately n times 1 minus e to the minus pi, because we love using this approximation in this section, minus I, which is equal to n times 1 minus e to the d over n, sorry, minus d over n I minus I. So then we can do something else. We can define a normalized frontier size. The normalized frontier size. Well, expected normalized frontier size, expectation of Fi divided by I is equal to 1 minus e to the minus d over n I minus I over n. So basically we're just normalizing the frontier size by the total number of nodes in our network. That's all we're doing. So what fraction of the network is in the frontier is our question here. And then we're going to let x be equal to I over n. So here is the variable that we care about doing a concentration inequalities on. So we're going to let this be the normalized number of steps. Number of steps. Well, when f of x is equal to 1 minus e to the minus dx minus x is the normalized expected size of the frontier. Where frontier here is in quotes, since it's the frontier of this modified process. And what can we say about this? So there are a couple things we can say. So if d is greater than 1, then f of 0 is equal to 0. Okay, so that's straightforward enough. And f prime of 0 is equal to d minus 1, which is greater than 0. So f is increasing at 0. Now this makes sense, right? So if you're just starting your process, well, the size of your frontier is getting bigger. But we also know that f of 1 is equal to minus e to the minus d, which is less than 0. So that means that, well, it's 0 in one place and going up, and negative at the very end when you finished your entire exploration process, which sort of makes sense, right? Because at the end of your process, you're decreasing your frontier size as you finish exploring your graph. But this together means that, so for some value, theta greater than 0 and less than 1, f of theta is equal to 0, just by the intermediate value theorem. And note, just as an aside, if d is equal to 2, the theta is approximately 0.7968. Okay, so you can't actually compute these, but it's not so important that we do. And we also know that the true BFS must be completed by the time f of theta is equal to 0. So we know an upper bound on the expected size of the connected component. Right, because the first time your function hits 0 is the same for your modified BFS and your true BFS. Now, the true BFS, it's not exactly well defined what happens after you hit the size of your connected component, but this modified BFS is well defined, and so we can use that to bound the true BFS. And so because we know that this modified BFS hits 0 at some point between 0 and 1, we know that the true BFS also must have done so. And so clearly this means that your component size does act like your process does stop somewhere between 0 and 1. This isn't so, this by itself isn't so interesting, because sort of intuitively you can reason that of course it's going to stop at some point, because at some point you're not going to hit any more nodes, right? But exactly when you stop, that's one of the interesting things here. And so for particular values of d, you can sort of see roughly when it would stop as a proportion of your entire graph. But that's of course not a very interesting bound. This is just sort of, in some ways, this is more like an existence type proof, that there is some like stopping point. So, but we can use the same setup of this modified breadth first search to actually bound the size of the connected component using the actual versus expected frontier size. So let's do that. So let's bound size of the connected component by using actual versus expected frontier size. So again, well, let's consider for d greater than 1. Well, then the expectation of f sub I plus 1 minus the expectation of fi. What is this? This is just the expected number of new nodes that you've added to your frontier after one exploration phase. So this is approximately equal to d minus 1 times I for small I. Okay, so basically at each step you're asking, well, how many additional nodes are added to my frontier? And that's of course something you can compute just because we're generating our edges on a as needed basis. And so you look at the remaining nodes in your graph, and then you just basically say, how many of these do I expect to add to my frontier when I explore one new node? It's basically just the expected number of new edges that you see. So this is because each new node adds d minus 1 new neighbors to the frontier. So we want to understand the probability that fi is equal to 0 for I less than n as the first such I marks the size of the first connected component. And what we're going to do now here is we're going to, let's see. So let's show that we don't stop after roughly c log n steps. So basically what we're going to say is if we're in the regime of where we've already gone c log n steps, then chances are we're not going to stop anytime soon. And what that's going to show is that the connected component must either be small or this big, or at least this big. So it's going to rule out the intermediate size of connected components. And to do this, we're going to use a number of approximations. So it is going to be a little bit hand wavy, but these are things that you can, but like this entire section has been a little bit hand wavy with asymptotics. So for small I, the probability that a vertex is undiscovered is equal to 1 minus d over n to the I, which is approximately I dn. Okay, everyone roughly happy with that? Because on each of your original steps, this is basically this is taking a union bound over the chance that something's undiscovered, rather than actually explicitly computing it. So now the number of discovered vertices is approximately equal to a binomial of n and id over n, which is approximately equal to a Poisson process with parameter id. Okay, so basically we're approximating. So for those who are not so familiar with these approximations, basically what we're just saying is that when you have, if some event happens about 0.001% of the time, and you run that event twice, then chances are you have approximately 0.002% chance of it happening. Even though that's not quite the right percentage, when you're in the small number regime, that approximation is roughly close enough. And you can use these other approximations in those sort of regimes. So this means that the probability that k vertices discovered by step I is approximately equal to e to the minus di times di to the k over k factorial. So this is just the Poisson approximation that we're using. And note that what we need is we need exactly I vertices discovered by step I. Because if we have more than that discovered, well, then we haven't concluded yet. So fi is not equal to 0. If we have less than that number discovered, well, it's still not concluded because that means that we concluded earlier. So we need exactly I vertices discovered by step I. So the probability is approximately equal to e to the minus di times di to the I over I factorial, which is approximately equal to, with our usual approximations, e to the minus di, d to the I to the I to the I. It's really confusing to keep on writing I to the I because I keep on thinking complex numbers, but these are not complex numbers. This is just an index. E to the minus d minus 1 I di, which is equal to e to the minus d minus 1 minus log d I. So for d is not equal to 1, d minus 1 minus ln d is greater than 0. And this is just by calculus. Plus the probability drops exponentially with I. So what are we saying? We're basically saying that the termination probability, so the chance that we're going to stop after you've gone a certain number of steps, drops close to 0. So long as we're in the approximation regime where this works. Probably for I greater than c ln n, for sufficiently large, c is little o of 1 over n. Okay, so if we are in the regime where we can do all these approximations, and I is at least c ln n for some sufficiently large c, then you're not going to stop. Intuitively, what we're saying is that once you've explored a big enough region, then you're unlikely to stop until you've explored basically everything. But this approximation doesn't hold when you've explored nearly everything because this is a small I approximation. But so for the small I approximation, you're not going to terminate. So for what let me write that down. So unlikely to terminate before the Poisson approximation fails. Fails if it is already omega ln n. Okay, so basically what we're saying is that this now rules out intermediate size components. Once you get to omega of ln n, then you're likely to keep on going until you've hit most of the graph. There's of course some chance that you end pretty early on, because if like just by chance your first couple nodes don't discover very many other nodes, then the process can end early. And it can end late because, well, at some point this approximation fails and you've explored the entire connected component or the entire graph. But in this intermediate regime, around log n, you're not going to stop. So now on the other hand, for I near n theta, we know that, am I running out of time? No. Near n theta, we know that the expectation of f sub I plus 1 minus the expectation of fi is equal to alpha times I minus n theta for some proportion alpha. And this is because there are only I minus n theta vertices left in expectation to explore. And each step discovers these with probability proportional to the stuff that's remaining. You could probably compute alpha, but it's not really so important for our purposes. And so for I near and theta, so remember, originally we were looking for very small I, and so that's when the Poisson approximation held. So now for I near n theta, we're going to use a different approximation. We have the binomial as our starting point, but there are other approximations of the binomial, right? And which would be a statistician's favorite approximation of the binomial? What's your favorite approximation of the binomial? Yes, Gaussian. Yes. No, I'm serious. That is the correct answer. So because when you have a binomial, if you flip the newly random variables enough times, it looks vaguely Gaussian, right? So central limit theorem and all. And so we can approximate it by a Gaussian. So we're going to approximate via Gaussian, which falls off exponentially with the square of the distance. The square of the distance from the mean. And so here, what we're taking advantage of is that the binomial distribution n ID over n is approximately equal to the normal distribution ID times 1 minus ID over n. And we know that ID times 1 minus ID over n is approximately equal to theta d times 1 minus theta d, which is approximately n, roughly speaking. I'm playing really fast and loose here. But thus, to have a non-vanishing probability, we need k to be less than or equal to root n. So the giant component is in the range n theta minus root n and n theta plus root n. Okay, so I've been playing really fast in this sort of approximations here. But the basic idea is that in the regime where I is very small, we can approximate it with this Poisson distribution. And when you approximate it via Poisson, what you find is that for small I, once you get past log n, size of your frontier, then you're unlikely to stop anytime soon. In fact, you're unlikely to stop while the Poisson approximation holds. And then, that means that once you get past that critical point, you keep on going. And if you keep on going for long enough, that approximation fails, and you can then instead approximate it by this Gaussian distribution, because that's what the binomial sort of turns into when you get close to the expected value. And once you do that in that regime, the probability that fi is going to be equal to the expectation of fi is going to be approximately n theta. It's going to be in a tightly bound range of variance n around the n theta. Did everyone follow all that? So what have we shown right now? We have not yet shown that there exists a giant component. All we've shown is that if there is a component that is bigger than log n, it has to be really big, around the order of n theta. So around order n. Whereas if it's really small, it has to be smaller than log n. So we've basically bounded it away from these intermediate size things. Because remember, like in this regime, what we're trying to prove is that you have one big giant component and you have a bunch of small components that are around order log n, or smaller than order log n. So what have we just shown? What we haven't shown is we haven't shown the existence of this giant component. So you can imagine that all of our argumentation was correct, but that you just never get to a giant component to begin with. Maybe everything terminates long before you get there. And that's a reasonable guess. And so we have to prove that that's not the case. So what did we just show? We just showed that components are Euler. I mean, when I say show, I mean show with high probability, of course. Are Euler O of log n, so smaller than log n, or omega of n. So at least as big proportionally as the entire network itself. So now let's prove that G of NP with P equal to 1 plus epsilon over n. So earlier we were just saying that P is some D over n. We didn't specify exactly what D was, except we characterized in the context where D is greater than 1. So now let's assume that P is at least epsilon bigger than 1 over n. So this has a giant component with high probability with 0 is less than epsilon is less than 1 over 8. And note, for larger epsilon, this only increases your component sizes. So this here is a technical condition. So epsilon doesn't have to be less than 1 over 8. We're going to prove it for epsilon in the range between 0 and 1 over 8, because that makes the proof simpler. And clearly, it's pretty easy to see that if you're increasing the degree probability, you're not going to be making the giant component any smaller. Like you're only going to increase it, if anything. So for this proof, we're going to again use a graph search algorithm, but instead of using the breadth first search, which is what we did earlier. So earlier what we did is we took a node, we explored all the nodes of that node, and then we explored all the neighbors of that node, explored all the neighbors of that node, and so on, right? In this case, we're going to use a depth first search instead. So we're going to use a completely different search process to prove the existence of this giant component. So we're going to consider a depth first search. Let's call this DFS instead of BFS. And we're going to have a similar process. We're going to let E be equal to fully explored vertices, not edges. I'm just using this for E for explored. I'm not going to use the term E for edges anytime in this proof. U is going to be unvisited vertices. And F is going to be equal to the frontier of visited and still being explored nodes. And why do we need this? And it's because when you're doing a breadth first search, you finish exploring a node before you move on to some other node, right? But in the case of a depth first search, you don't do that. So what you do is instead you you explore one node, and as you're starting to explore it, if you find another node, you go there first. And if you see another node there, you go there first. And you don't come back until you finish exploring everything at the very bottom of the tree. More precisely, let's see, let's actually write down an algorithm so you know what I mean. So our starting state is going to be E is the empty set, F is the empty set, and U is equal to V, the set of vertices. And we're going to treat F is going as a stack. As a stack with VK as the active vertex. So for those of you who haven't had that much computer science, basically what we mean is that we're going to always look at this VK. So we're always going to look at the last thing we've added. So that's sort of what I was describing. You're always going to fully explore the downstream tree before you come back up to what you started with and finish exploring that. And then the process is going to be, well, repeat until U is equal to the empty set. If F is equal to the empty set, we're going to let F be equal to U, and U where u is chosen arbitrarily from our unvisited vertices. Okay, so note that in this case, we are actually just going to arbitrarily, we're not going to have this idea of red vertices. We are just going to arbitrarily pick some other unexplored vertex, or sorry, unvisited vertex. So if there's nothing left to explore, we're just going to start over somewhere else. And this is the case where f is not equal to the empty set. Well, then we're going to explore. So if there exists some edge bk u for u and u, and again, we can generate edges on the fly with probability p again. So you don't have to have pre-generated your graph. You can just look at each new hop as something that you do with probability p. So if there exists an edge there, then what we're going to do is we're going to remove u from u and push u onto stack f. So if there's an edge, well, then it's no longer an unvisited vertex. That's now going to become part of your frontier of visited and still being explored nodes. And then the next step, then you'll go to lat node and then look around. And then the first time you see an edge coming from lat node, then you go there, and so on. So what we're doing is we're repeat edge queries until one is true. Or we run out. We run out of new nodes. And if you run out, well, then that means that that's the terminus. And then you go up a step on the stack. So else, if there doesn't exist something like that, we're going to pop vk off f. So because we're finished exploring vk, and then we're going to add vk to e as the set of fully explored nodes. Okay, so now we've defined some other exploration process, and we're now going to characterize how long this exploration process takes. And using this, we're going to characterize the size of this giant connected component. And I think this is lemma 8.7 in your textbook. I've been really bad about putting like theorem numbers. But anyway, so after epsilon n squared over 2 edge queries with high probability, the size of the explored set is less than n over 3. What do we mean by edge queries? We just mean like each time you ask your graph, do you have an edge here? And you can think of each of those as flipping a coin, because each time you ask, the graph generates, oh yes, I have an edge there with probability p, or no, I don't have an edge there with probability 1 minus p. Well, let's prove this. So suppose not. If not, then at some time, at some t less than epsilon n squared over 2, the size of E is equal to n over 3. And well, the size of f is less than or equal to the sum over I equal 1 to n minus, to t of I sub I, where I sub I is the Bernoulli indicator variable, a random variable corresponding to the ith edge query. Okay, because of course, each time you ask an edge query, you're asking, is this node in my frontier? And so clearly the size of your frontier is going to be less than or equal to the number of times you've done that, and the number of times that answer has been yes. It's going to be less than or equal to because the nodes can leave the frontier after you fully explored. But this is an upper bound, and that's less than or equal to epsilon n squared p with high probability. Why is that?
Sorry, remind me of epsilon?
Epsilon is the term we're using here. So I'll give you a hint. What's the expected value of the size of f? So what's the expectation of the size of f? Yes, and t is and so at time t, so the expectation is going to be less than or equal to epsilon n squared p over 2. right?
Okay, because T is not.
Yeah, and so what we're basically saying is that what's the chance that you're really, really far away from your expectation? So if I flip a coin, that has probability P of appearing 10,000 times, well, you have 10,000 expectation 10,000 P. What's the chance that you're going to have 20,000 P heads? And so that probability is very small. And so that's what we're using here. You can explicitly prove this with Chebyshev, but we're playing fast and loose with our bounds right now. And so this is less than or equal to 1/8 times n squared times 1 plus 1/8 divided by n. So we're just plugging stuff in here, which is equal to 9/64 times n, which is less than n/3. Plus, at time t, the size of the unexplored is equal to n minus the size of the explored minus the size of the frontier, right? So just they add up to the total number of nodes. And let is greater than or equal to n/3. Because the size of explored is n/3 and the size of the frontier is less than n/3. So you have to have more than n/3 unexplored. But note that by construction, there must be an edge. Oh, sorry, there must be no edges between U and E. Right? Because if they're worried, they would be in the frontier instead. So but that means at least E over U, which is greater than n squared over 9 queries. Right? Because in order to know that there are no edges, you had to have done those queries. So that means that T is greater than or equal to n squared over 9. Now this is a contradiction. Because T is less than or equal to epsilon n squared over 2, which is less than or equal to n squared over 16. And therefore, we know that this proves this lemma. So this is just a technical lemma about the sizes of these, about the size of the set of explored after some number of edge queries. Okay, let's see. And next, let's see, this is in lemma 8.8, which is another slightly technical thing. After T, which is equal to epsilon n squared over 2 edge queries, with high probability, the size of the frontier is greater than or equal to epsilon squared n over 30. And note that the epsilon, like the power of 2 is not a typo there. So I do mean after T is equal to epsilon n squared and F is greater than or equal to epsilon squared n over 30. And it's going to, the proof is going to take a similar form. So we're going to make use of a turnoff bound nearly n, I think. Yeah. Actually, we might not use a turnoff bound. No, we use a turnoff bound. Yeah. So let's suppose that the size of F is less than epsilon squared n over 30. We're going to then find a contradiction that shows that this can't be the case. Well, if that's the case, then the size of U is going to be equal to n minus E minus F, which is greater than or equal to n minus n over 3 minus epsilon squared n over 30, which is greater than or equal to 1 if n is greater than or equal to 2. So what does that mean? That just means that the process hasn't stopped. So depth first search active, because you still have a node that you've not explored, and so you can keep on going. So we haven't stopped our process yet. And we know that E plus F is equal to the sum from I equal 1 to T of I sub I, because you need yes queries to move edges from U to F. So this is the same as our less than or equal to here earlier, except here they're actually equal since we're including both the set E and the set F. So that's equal to this summation. And therefore and we know that the expectation over I equals 1 to T of I sub I is equal to epsilon n squared P over 2, which is equal to 1 plus epsilon times epsilon n over 2, which is equal to epsilon n over 2 plus epsilon squared n over 2. And so therefore, with high probability, the sum is greater than or equal to epsilon n over 2 plus epsilon squared n over 3. And this is by turnoff, by a variant of turnoff. Thing. And again, all we're basically saying is that it's unlikely for it to be very far away from its expectation. And so, and you can be slightly more careful or less careful with how close it is. So like if we were still back in the sketching section, we might like explicitly compute all the delta probabilities of failure here. But we're not. And so we're just saying that with high probability, you're likely to be in this regime, especially as n grows asymptotically. And so this gives us some bound on these sizes. This implies that the size of our explored is greater than or equal to epsilon n over 2 plus epsilon squared n over 3 minus epsilon squared n over 30, which is equal to epsilon n over 2 plus 3 epsilon squared n over 10. So note that these constants have been chosen magically to work out in this proof. So like the constants, like the value over 30 here, like these are the reasons we chose these, so that they would work out. But note that again, the size of E times the size of U is less than or equal to epsilon n squared over 2. And so the size of E times n minus the size of E minus the size of the frontier is less than or equal to epsilon n squared over 2. And in the range, so when E, the size of the explored, is in the range epsilon n over 2 plus 3 epsilon squared n over 10 and n over 3. So when it's more than that, the left value, but less than the right value, for f fixed, we know that the size of f is less than or equal to n over 3. And when we fix that, we can take the derivative with respect to the variable that is E. So now all we're going to do is we're going to take this derivative, d over the absolute value of the size of E, of this this thing, n times n minus E minus f, which is equal to n minus 2 E minus f, which is greater than or equal to 0. So we know that this thing increases with E, which is perhaps unsurprising. So basically what we're saying is that the number of explored elements times the number of unexplored elements, like that product, is increasing when you haven't explored that much yet. So when you haven't explored very much of your graph yet using the depth first search, then the total number of the product of the size of your explored and your unexplored increases. Well, if that's true, then that means that this product is greater than or equal to epsilon n over 2 plus 3 epsilon squared n over 10 times n minus epsilon n over 2 minus 3 epsilon squared n over 10 minus epsilon squared n over 30. I'm not going to show this explicitly, but this turns out to be greater than epsilon n squared over 2 just by lots of ugly algebra. And this is a contradiction. So with high probability, the size of f is greater than or equal to epsilon squared n over 30. And note that, importantly, f is a connected component. Note that the frontier is a connected component. So what we've just shown is that we have a connected component that is large. Okay, so this proves the existence of a, so in the first part of today's lecture, I guess we're running out of time. So just to quickly summarize, I have one more proof, but that will wait until next Wednesday. So what we've proven so far is that the size of that components in this regime are either small or very big. We just proved that there is a really big one, and you can show that there are small ones. We're not going to do that in this class. And on Wednesday, we're going to finish up this section by showing that there's only one big component. So if you, it's impossible to have two big components, because if you were to imagine having two big components, they would be connected to each other just because they have so many cross edges, basically. And so we'll do that on Wednesday. And with that, I will end class for today. Any questions? I know the proofs today were really technical, but I really wanted to just show you some of these less trivial versions of the proofs. So like the proofs yesterday were all like straightforward applications of first and second moment. Here we had to define some complicated variable and then use related methods to really bound these different things to get phase transitions.
Could you go on the second to last proof, just for a second?
Second to last proof. This one?
Yeah. I don't have any specific questions.
Oh, okay. Yeah. So I'll just say, so I also have, these proofs are all from your book. So they are all in your textbook. And I have a version of the free lecture notes, which is online now, which I started putting online. And I will, of course, put down this version of the lecture notes online afterwards as well. Are there any questions in chat? No, let me go ahead and end the chat, Led.